All right, everybody. We are here to do 2.7 solving equations in one variable, and we're going to talk about rational equations. And we know that every rational equation can be written as in the form of f of x over g of x. Yesterday, we were talking about how this can be n of x over d of x, but really in the general sense, we have some function f of x over g of x, same as n of x over d of x. And what we could say is if f of x and g of x are polynomial functions with no common factors, then the zeros of the numerator are the solutions of the equation. Now, that's something very similar to what we did the day before. We were talking about how the numerator also, if we made it equal to 0, we would find out that that was the x-intercept. So just like how we used before, remember solutions, factors, zeros, roots, they're all interchangeable. They all mean the same thing. Here we have ways of clearing fractions procedure. Well, what we do is we're going to find the LCD, the least common denominator. So find the LCD of all terms. And we'll look at these in the example that's coming up in a second. On top of that, we're also going to multiply each side. Multiply each side by the least common denominator. So by the LCD. Now, when we do solve rational equations, we can have something called extraneous solutions, which we've experienced in Algebra 2, and that is just where we get an answer and we plug it back in, we get a no solution, or something that just doesn't make sense, a false statement. Oops. And what happens here is that what we can say is when we multiply or divide an equation by an expression containing variables, the resulting equation may have solutions that are not solutions of the original equation. For this reason, we must check each solution of the resulting equation in the original equation. So as I was saying, that's just us taking the values that we get and seeing if it actually works back in the original problem. So when we're solving examples, here we have example 2a, and what we have to do is solve for x, where we have x plus 6 over x equals 5. Now, we could follow the rules here of find the LCD of all terms, multiply each side by LCD. But I kind of want to go through what we've done in the past, and that is, let's just find the least common denominator on the left side. There's no fractions on the right side. Let's leave the right side alone for just a moment. And what happens here is we get something like x plus 6 over x. And we go, okay, well, the denominator on this x is 1. Well, we think about what does the denominator need to be just like this one? Well, we're like, oh, it needs an x. So we're going to multiply the numerator and denominator by x. And what we end up getting is x squared over x plus 6 over x is equal to 5. And now that they have the same denominator, we can bring them together. We can say, okay, this is x squared plus 6 over x is equal to 5. Now I can finally get rid of my denominator. That's where we can multiply each by the least common denominator. We're going to multiply this x to the other side. So I'll draw an arrow here. I'm going to multiply to that 5. And I get x squared plus 6 is equal to 5x. And I have a quadratic. The only way we solve a quadratic is by setting it equal to 0. So I need to subtract 5x to both sides. And I get x squared minus 5x plus 6 is equal to 0. In doing so, then what we can do is say, okay, this factors to be x minus 3 times x minus 2. And that's equal to 0. We branch it out and we find out that x minus 3 equals 0, x minus 2 equals 0. Therefore, x must equal 3 and x equals 2. And we've solved for x. And these are our answers. Let's practice that again doing example 2b. Well, Here I have x plus 1 over x minus 3 is equal to 1. We do the same kind of logic. I go, okay, well, I need to get common denominators. This denominator over x is 1. And I go, what does this 1 need to be like an x minus 3? Oh, I just need to multiply the top and bottom by x minus 3. So that leaves me with x times x minus 3 over x minus 3 plus 1 over x minus 3 is equal to 1. These have the same denominator. I can also, at the same time as I'm getting the same denominator, I can also distribute the x into that parentheses. So what I get is x squared minus 3x plus 1 over x minus 3 is equal to 1. I then want to make the denominator go up to a numerator. Well, the only way I can do that is if I multiply this x minus 3 to the other side. And what I get here is I get x squared minus 3x plus 1 is equal to x minus 3, because 1 times x minus 3 is just x minus 3. Again, I have a quadratic. So what I want to do is I want to get it equal to 0. So I'll subtract by x to both sides, and I'll add 3 to both sides. Once I've done that, I get x squared minus 4x plus 4 is equal to 0. And this factors out to be x minus 2 times x minus 2, and that's equal to 0. But since they're the same equation, I don't need to branch them out. I can just write the equation once. X minus 2 is equal to 0. Therefore, x equals 2. And I solved another problem using rational functions in my equation. As for example 3, here is something where we're going to get some extraneous solutions, and we need to possibly check our answers. So we go through this problem and realize, oh wow, we have 3 fractions. One thing we should always do is make sure that every set of values that have x, we need to make sure they're all factored out as much as possible. If we do that, then we're going to be able to solve these problems a lot quicker. And what I notice is here is that x plus 2, those are completely factored. 4, x minus 1, completely factored. 2 is completely factored, but x squared minus x is not completely factored. I can rewrite x squared minus x to be x times x minus 1. I can factor out an x because they have an x in common. So since they have an x in common, what I can do is I can now say, okay, this is going to be x plus 2 over x minus 4 over x plus 1, or sorry, x minus 1 plus 2 over x times x minus 1, and this is all equal to 0. Let's recall we need to get common denominators in all the fractions. So what I do is I just go through a thinking process. What does this fraction need so it can be like the rest of them? Well, it has an x, but it needs an x minus 1. And this one has an x and an x minus 1. So this one already has everything of the other two. So this one seems like it's good. These ones are missing pieces that look like this one. So I know I need to multiply this one by an x minus 1. So top and bottom. So I get an x minus 1 and x minus 1. And then I go, oh, well, this one here, this x minus 1 needs... Now, this is not a plus 1. Like I said, I made a mistake. This is supposed to be an x minus 1. Oh, it needs an x. So what I'm going to do is I'm going to multiply by x to top and bottom as well to this fraction. So after I've done that, I should have x minus 1 times x plus 2 minus 4x plus 2. All of that is over that common denominator of x times x minus 1, and it's all equal to 0. What I need to do next is I need to FOIL out these terms. And I want to share this out to be x squared plus x minus 2 minus 4x plus 2 is equal to 0. And what happened? And then this is all over x times x minus 1. And what we can do here is we can just say, okay, I'm going to multiply these to the right. So let me show this in a different color. Let's put this in blue. Multiply that over. But 0 times this denominator is just 0. So we're just left with this numerator. So we can combine like terms. And what we have is the -2 and the +2 will cancel out. And this x minus 4x gives me x squared minus 3x is equal to 0. They have an x in common. We can factor out an x. And we get x times x minus 3 is equal to 0. I branch them out. I find out that x equals 0 and x minus 3 equals 0. So this means that x equals 3. There's my answers. However, I need to go back and check my answers and see if I get any false statements or if I get any situations where the denominator becomes 0. I know immediately that 0 does not work. Why? Because here I have an x and an x squared minus x. If I plug in 0 here, I get 0 minus 0. 0 is in the denominator. So what I find out is that I cannot use x equals to 0 as an answer. So because of that, my only answer actually is x is equal to 3. Now, likewise, we can do this in example 4. We have a very similar problem, but now this time the left side and the right side have x's. And we're going to use an old technique that we used back in Algebra 2. Now, the rules still apply. The first thing is make sure everything is fully factored. 2x plus 3, nothing more can factor. X minus 1, nothing more can factor. 10 can't factor. 2x minus 3 can't factor. X plus 1 can't factor. But x squared minus 1 can factor. We need to keep in mind about a squared minus b squared. And that's equal to a plus b times a minus b. Remember, our difference of squares. I'm telling you guys time and time again, difference of squares keeps popping up. So this is just an a squared minus b squared. We can rewrite it. And this can be the left side be 2x plus 3 over x minus 1 equals to 10 over x plus 1 times x minus 1 plus 2x minus 3 over x plus 1. Now, what I recommend here is just focus on the side that still has the addition of fractions. So we're going to focus on this right side and let's get a common denominator here. Well, we go through it and we realize, okay, they both have an x plus 1, but this one's missing an x minus 1. So we need to multiply x minus 1, the top and bottom for this one. All right. So what we have to do now is we get 2x plus 3 on the left side over x minus 1 is equal to 10 plus 2x minus 3 times x minus 1 over x plus 1 times x minus 1. Now, something that I mentioned last year, and we got to remember this year, is that when we have something like this, an equation of a fraction equaling a fraction with variables on the numerators and denominators, we have something that's called a proportion. And a proportion can be simplified before we go any further. Well, what we can do is we have this situation where, let me box this over here so we can see it separately. Whoops. And what I have is a situation where I have A over B is equal to C over D. And the way I can cancel these kind of problems is I can cancel vertically. I can do any simplification, any reducing vertically. But because of a proportion, I can also cancel horizontally. So if there's something in common horizontally, I can cancel there as well. So what I have here is I have an x minus 1 and an x minus 1 horizontally that cancel. Now, some of you might be like, well, Mr. Arias, well, why not the x minus 1 in the numerator? Because there's this plus 10. If there was no plus 10 here and it was just like this, then yes, we can cancel vertically. But because of this plus 10, we can't do that. So this simplifies to be 2x plus 3 is equal to 10 plus 2x minus 3 times x minus 1 over x plus 1. With that, we're going to multiply the x plus 1 to the other side. And this gets us 2x plus 3 times x plus 1 is equal to 10 plus 2x minus 3 times x minus 1. We need to FOIL and simplify. And what we get is we get 2x squared plus 5x plus 3 is equal to 10 plus 2x squared minus 5x plus 3. So next thing we're gonna do is we have two quadratics on both sides. We just need to set ones of the equation, like on one side, set it equal to 0. So what I'm gonna do is I'm gonna subtract 2x here, subtract 2x squared, and subtract another 2x squared. I'm gonna subtract 3, and what happens here is these cancel out. So I'm left with 5x is equal to 10 minus 5x. Well, I can add 5x over to the other side. So let me change that in color so we can see what we're really keeping here. Plus 5x, and we can subtract 10, and now what we have is 10x minus 10 is equal to 0. They have a 10 in common. We get 10 times x minus 1 is equal to 0. And what we can do now is say, okay, the 10 can be divided that to the 0, or we could add a 10 and then divide it by 10. That's a much easier way. Not sure why I did this. We can just add 10. I apologize. And we get 10x is equal to 10, divide by 10, and x equals 1. Sorry about that. So we get x equals 1. And what we have to do now is make sure that this is a solution. We only got one solution here. If we get a 0 anywhere in the denominator, this doesn't work. Well, immediately if I plug in 1 here, I get a 0 in the denominator. We can find out that that doesn't work. So we know x equals 1 cannot work. So our answer here is no solution. Okay. So ignore this step. I'm not sure what I was thinking there. I mean, we could get the right answer, but it wasn't necessary. So just go follow along with when I just add by 10 and then divide by 10 there. Now we're going into example 5. It says, how much pure acid should be added to 50 milliliters of a 25% acid solution to produce a mixture that is 60% acid? Now, the one thing that we have to know here, and I'm giving it to you here now, is that we have a mixture, right? So what happens here is we find out that we have milliliters of pure acid over milliliters of mixture is equal to concentration of acid. Now, that is something that I have to give you. So I'm giving that to you now. This is a formula for it. And now with that knowledge, we can say, okay, well, I know that x can be equal to, we'll set x to be equal to the number of milliliters of acid to be added. And I'm even told here that 25% of my acid solution of 50 milliliters is going to be what gives me pure acid. Is at least the percentage of 25% of pure acid. So I can say that 0.25 times 50 is equal to milliliters of pure acid in 25%. So that sets up an equation for me. I can say x plus 12.5 is equal to the milliliters of acid in mixture. And we can say that this is, then we can also say that x plus 50 is equal to the milliliters of resulting mixture. And what we really can say about these two equations is that this is part of the mixture, and this part is the whole mixture. So this is the part where it's just the acid is a part of the mixture, and this is the whole thing afterwards. So what we can do is that the question's asking us, let's read the question one more time. It's asking us, how much pure acid should be added to 50 milliliters of 25% acid solution to produce a mixture that is 60% acid? So we only want 60% acid. Well, let's plug in what we have. Milliliters of pure acid. That's our equation here that we're going to get from the x plus 12.5. And the milliliters of the resulting mixture, that's the whole, over x plus 50. And we're going to have it equal to the concentration that we want. 60% is the concentration. So I get x plus 12.5 over x plus 50 is equal to 0.60. I multiply the x plus 50 to both sides. And I get x plus 12.5 is equal to 0.6x plus 30. Okay, distributing the 0.6 into x and into 50. And I solve for x. And by solving for x, I get 0.4x is equal to 17.5. Divide by 0.4 to both sides. I get x is equal to 43.75. And what I write as my answer is that we need 43.75 milliliters of pure acid should be added. So 43.75 milliliters of pure acid should be added so that we get the compound that we were asking for, the 60%. That's our answer for that problem. Moving on to example 6. It says, find the dimensions of the rectangle with a minimum perimeter if its area is 300 square feet. Find the least perimeter. So here, in this problem, we have a situation where we know that the area of a rectangle is the length times the width. So length times width. And we know that the perimeter is going to be 2 times the length plus 2 times the width. Those are just the formulas for the area of a rectangle and the perimeter of a rectangle. In doing so, we know that the area is going to be 300, and we know that there's some length times the width. Now, what we have to do is use this formula to solve for L or W to plug it into our perimeter, because we're trying to find the least perimeter. So it doesn't matter which one we technically pick, but let's solve for L. Let's divide by W to both sides. And I find out that L is equal to 300 over W. I take this L and I'm going to plug it in to this L here. And P now is going to be equal to 2 times 300 over W plus 2W. I take this function here and I expand it out. I expand it out and I get a common denominator if I need to, but not really. Well, all I need to do is just multiply this out and I find out that P is equal to 600 over W plus 2W. And it's even telling me the key word here, minimum. Remember, what is a minimum? It's a valley. Remember, we talk about peaks and valleys. So if I put this function in the calculator, graphing calculator, 600 over W plus 2W. Now I need to get the right window and so forth. But essentially with getting the right window, my graph looks something like this. This is X comma Y. I get a function that looks something like this. And I get a minimum by tracing and doing the second calc or second trace button, and I find the minimum here. And I find that the coordinate is 17.32 comma 69.28. So this is my minimum. What this tells me is I need to interpret this. Well, then it's telling me that, remember, I'm having something that's L and W. So one is my X, one is my Y. So I know by this information, I can say the width is about 17.32 feet, and the minimum perimeter is about 69.28 feet. And I got that from my graph once I found the minimum of that parabola. Okay, it's not exactly a parabola, but it looks similar to a parabola. But if I were to like multiply it out and get like a common denominator, I'd get 600 plus 2w squared over w. And it's a rational function, so it would look a lot like a parabola, but it's not exactly a parabola. One last example, and we have designing a juice can. It says the Acme Can Company is marketing a new 1-liter cylindrical can for an orange juice concentrate. Find the radius and height of the can if the container will have a surface area of 1,000 centimeters squared. It's telling us, note that the volume equals pi r squared h. The surface area is 2 pi r squared plus 2 pi r h. And we're told that 1 liter is equal to 1,000 centimeters cubed. So we're given all the information we need in this problem. So what we can do is we can say, oh, okay, well, I know the volume is going to be equal to pi r squared h. And I also know that I'm told that the volume is 1 liter. And I know that 1 liter is 1,000 centimeters cubed. So I can say that this is 1,000 is equal to pi r squared h. And it's saying find the radius and height of the can if the container will have a surface area of 1,000. So we also know that the surface area is also going to be 1,000. But what we need to do is solve for r or h here. And right now it's a lot easier to solve for h. We just need to divide pi r squared. So we find out that h is equal to 1,000 over pi r squared. And we can use this h and plug it into the s formula and solve for r. So well, that's what we're going to do. I'm going to get, from this formula, I can say that s, which we're told is 1,000, surface area of 1,000. We can say 1,000 is equal to 2 pi r squared plus 2 pi r times this h value, 1,000 over pi r squared. And we can simplify this out. The way we can simplify is go, oh, you have a pi in the numerator, pi in the denominator. Pi's cancel. R in the numerator, r squared in the denominator. R cancels and the squared cancels. And I'm left with 1,000 is equal to 2 pi r squared plus 2,000 over r. What I did was I multiplied the 2 times 1,000, and it's over r. And now we need to solve this equations. Okay, so I know that what happens is that I need to make sure that I'm finding the radius and the height of the can if the container. So I'm trying to find the radius and the height if the container will have a surface area of 1,000. The volume is also equal to 1,000. So I can say that these two equations are essentially equal to each other. Or like what? So then if they're equal to each other, we're finding out when does these two values equal the same. So I have two equations. I can say that I have y equals to 2 pi r squared plus 2,000 over r. And I also care about when y is just equal to 1,000. When it's equal to 1,000, I get these two statements. So I can plug this into my graphing calculator of both equations, and I get a graph that looks something like this. Plug in the graphing calculator, and I get equations that look similar to this, where I have, this is a very rough estimation, but I get a line of 1,000 that crosses through, and it crosses at 2 points. Point there, and a point there. And the coordinates are, this one would be 2.054, comma 1,000. And the last point would be 11.462, comma 1,000. Now let me repeat that one more time. I chose this equation here because I'm trying to find out essentially, when is it 1,000 twice? Because of my volume and my surface area. So my window of this is essentially on the graph is going to be somewhere. I'll tell you guys when you graph it, you can graph it between something where you have 0 to 50 to 0 to 12, 1,200, and it'll fit in here. Or I'll show you guys on Desmos in just a moment, and we could just graph it through there. But because of this, we can say, oh, okay, well, if I plug these values for my R, the 2.054 and the 11.46, back into this equation, I can find my H's as well. In doing so, I find out that size number 1, plug in this R, the 2.054 into here, I find out that my R was the 2.054 centimeters. And my H is not going to be 1,000. Remember, this is when I'm trying to find out what R's of this function equal 1,000. I could have solved this. I could have got common denominators, multiplied it by R, done all that fun stuff. Or I could just, what I did was I used a graphical approach. I found out, when does this function equal to 1,000? Like I said, I will graph this in just a moment so you guys can see. And I get 75.44 centimeters for the height. Like I said, that's for when I plugged R here into this. And size number 2 is going to be R equals to 11.462 centimeters. And my H is going to be equal to, plugging in the 11.462 centimeters here, I get H to be 2.42 centimeters. And I get my answer there. Now, let me open up Desmos so we can see what this looks like. So, going to Desmos. Make sure we're good here. And if I type in my equations here, I type in 2 times pi x squared. I'll use x squared because the graphing calculator is not going to know that what R is, plus 2,000 divided by x. And I need another equation. Well, actually, I need to make y equal to this. I believe Desmos needs the y. So y equals. And let's say y equals to 1,000. Oops, sorry. Let me change back the desktop. And I need to put a window here. Let's do from 0 to 1,200. And I also want to do, actually, I don't think that's the window settings, but let's see. Done. And here, let's go from 0 to 50. And the y-axis from 0 to 1,200. And we get this graph here. This is the part we care about the most. And if we zoom in here and I click on this spot, we should get the coordinate of 2.054 comma 1,000. And if I click on this coordinate, I get 11.462 comma 1,000. So again, Just to repeat one more time, what I did was I said I wanted to solve for this equation here. So I literally graphed this part of the function, and I graphed the other part of the line y equals 1,000, and just found where it intersected. I can use Desmos for that, or I can use a graphing calculator, and I can show you guys in class how to do that. All right. So there's your there's section 2.7. Let me know if you have questions in class tomorrow.